And what we're going to do here is that we're going to lecture on applying Gauss's law to charged cylinders. Now, we're going to use the same process as before. And you really want to, this is one of the iconic problems, okay? This is one of the iconic problems. So we really want to look at this and do this well. So here we go. So you could see here that I did in the problem solving strategy. So I'm always looking at this. So what do I mean by a charged cylinder? So when I think about a charged cylinder, we want the E field everywhere. So what I imagine here is that this is a very long cylinder. So no end effects can be seen. If we can see the ends, then it's not a symmetric situation. So when I say the word very long, I'm really thinking that I'm so close to the surface that it looks like an infinite cylinder. So there's a couple of views that I want you to think about. So here's my cylinder. So let's say that I have my cylinder here. And what I'm only showing you is a piece of the cylinder. So when I'm looking at this guy, I'm only looking at a piece of it, but it goes on for a very, very long ways. And I know that, people always say, well, there's no such as an infinite cylinder. Well, that's not true. You have wires in your house that are very long. So if I look at the radius of the wire compared to the length of the wire, since the length is so much longer, I could treat that wire as an infinite cylinder. And so when I look at this guy, you got to be careful here. I do see charge on the cylinder, right? Here's charge. Now, what you're seeing here is that there's also charge at the end, right? There is charge here, but it's so long, we don't account for it. Oops. So remember, I'm not going to worry about this thing. So now, what are some of the details here? We know it has some length that we're going to look at. And we know it must have some radius r. Okay, so this is a side view. But now, how am I going to look at Gaussians here? So now I'm going to focus on Gaussians. So if I look at my Gaussians, I'm going to think about little r greater than big R. So now if I have a front view of this thing, it's looking like this here. So this is my front, maybe the front, the side view of it, I said front. So we know that there's charge on this guy. So now what I'm seeing here is that I'm going to put my Gaussian where? On the outside. So when I look at this guy, what do I see? Well, I see that the Gaussian has a radius r, and now the cylinder has a radius big R. That's where I want to calculate the field. Now, what happens if I have a Gaussian that's inside? So now little r is smaller than big R. So now I'm going to draw this larger. And so again, here's the end view of this guy. And of course, again, I have a uniform charge distribution. And what we're going to do here is that we're going to choose our Gaussian inside of here. So when I choose my Gaussian inside of here, what you're seeing here is that I'm only getting partial charge. So when I look at this, I see that that's my radius r, and then this is my radius big R. So we want to calculate the field outside the cylinder, and we want to calculate the field inside the cylinder. So let's do that. So what we're going to do here is that before we do that, what I'm going to focus on is that I need to pick a good Gaussian surface. Okay. And you could see that the Gaussian surface, in order, if I ignore the ends, it has to be the shape of a cylinder here. So before I go into talking about this thing here and getting into the details, I want to calculate the Gaussian outside, excuse me, the E field. So now what we're going to do here is that we're going to check. So the first thing here is we're going to be outside the cylinder, which means that little r is greater than big R. So the first thing I got to do is I got to pick a Gaussian surface. So here I go. So the first thing I'm going to do here is that I need my Gaussian. That ignores the end pieces because it's not symmetric there. So we have to ignore the end pieces. So now here I go. So when I look at my Gaussian, I'm going to redraw my cylinder here, right? Just as before. So I'm going to draw the cylinder again. And here I go. So I'm going to pick my cylinder like this. And again, this is very long, so that I don't look at the end. So now this guy has enclosed charge. So now here I come with my Gaussian. So my Gaussian then, it's going to look like this. And so you're seeing here is that this guy has a radius r, and this one has a length L. And so when I look at the field of this guy, I can see that the field is pointing like this. Oh God, not there. It's pointing through the flux through the cylinder. The cylindrical Gaussian looks like this here. So then this is the direction of my E field. So now what I see here is that there are two areas. There's the area perpendicular to the curved wall. So I'm going to call that dA, and note that there's an area perpendicular at the ends. So what you're seeing here is that there's my Gaussian. And so what I'm going to focus on is that I'm going to focus on the flux. So if I focus on the flux, we then see that the flux goes through two pieces. One is the end pieces and the curved walls. So when I'm seeing this, this is what I'm seeing here now. So let's focus on the end pieces. So at the end pieces, we see that this is the cylinder, this is the side view of the end right here, right? This is the side right here. And what you're seeing here is that when I look at the E field, the E field is doing what? It's moving from the inside going out like this. So this is the direction of the E field. Now remember, we're not allowing for the end pieces to have charge on it so that it contributes. And then look at A here. So if you look at A of the ends, you could see that they are perpendicular, that it's at 90 degrees. So immediately I see that the flux of the ends, which is E, of the ends, is then going to be E dot dA of the ends, and this is automatically zero. There is no flux going through the Gaussian surface right there. So now that I got the end piece, then what I'm going to do here is that I'm going to focus on the curved walls now. So here's the end piece, here's the curved walls. So now what you're seeing here is that if I now look at the end view, so from the end view, I see that my Gaussian looks like this here. So I have charge here. And so my Gaussian is like this. So if this is my Gaussian and that's at R, what you're seeing here is that the flux through the Gaussian is now looking like this here. So that means the field is diverging at that point. So now I look at the field there, and now what you're seeing is that the area vector of the curved walls, it's parallel to the electric field. So when now I look at the flux here, you're seeing that the flux of the curved walls now is going to be like this. I'm going to have E dot dA, but now the area has to be of the curved walls. So when I look at this thing, now I can see here is that this is a constant. Everywhere on this surface, the electric field is a constant, so I can pull it out. So then this then becomes the electric field for little r greater than big R times the area of the curved walls. So now I can look at the net flux. So the net flux is then going to be this. So the flux of the cylinder has a flux of the ends plus the flux of the curved walls. But we already saw that these guys are perpendicular, so therefore they're zero. And then here, because they're parallel, there's a plus sign between E and dA. That's because we have a positively charged cylinder. If we had a negatively charged cylinder, then I would put a minus sign in here. So what that tells me now is that I have this, so then I know that this guy is going to be the E field for that times the area of the curved walls here. So if you look at the area of the curved walls, well, you got to think about it this way here. If I just look at the curved walls, what you're seeing here is that this is the circumference, and then the length of the cylinder goes like this. So if I just want the curved walls, then the area tells me that it must be 2 pi r times L. So therefore, the flux of the cylinder must be then E r greater than big R times 2 pi r times L. So now I have the flux. So now the next thing that I got to do here is I got to get the enclosed charge. So if I have a cylinder that has a total charge of Q, okay, so let's assume, so the cylinder has a total charge of Q. Clearly then, the Gaussian encloses all of that charge. So therefore, I know what the enclosed charge is right here. So now I apply Gauss's law. So if I apply Gauss's law, we get that the flux of the cylinder is equal to Q enclosed divided by epsilon naught, which then tells me that I get E of little r greater than big R times 2 pi r L, and then this would be Q divided by epsilon naught, which then tells me that little r greater than big R is then going to be 2 pi epsilon r, and it's customary to rewrite this as Q over L. Okay, that's just customary. This turns out to be the charged linear density. Let me rewrite it again. And it looks like this. So now I have my field here. Let me change the color. So we now have our field. Okay, and that's for the outside. Now what we're going to do here, so now that we got the outside of the cylinder, now we're going to go to the second piece, and we're going to go to, and we're going to go the inside of the cylinder, which now means that little r is less than big R. So here we go. Now, if I look at it from the end viewpoint, what do I see here? Well, maybe I should, let's draw it two ways just to make sure that we're clear. So now I have my cylinder. So if I look at this situation, I'm going to draw this large. So when I look at this guy, again, remember, this is very, very, very long. So when I look at this guy, I have the actual cylinder. So now what I'm going to do here is that I'm going to start putting in charge. And I think it's important that we put a lot of it so it's real crystal clear on what I'm doing. Okay. So now when I look at this thing, here's what I see. I'm going to choose my Gaussian to be inside the cylinder. And as I choose my Gaussian right here, you could see that it coincides here. So when I look at that, I'm enclosing less charge than the total charge. So when I look at my radius, I could see that this guy right here is my little r, and then my big R is this guy. So little r is definitely smaller than the inside of this thing. So again, when I look at this guy again has a length L. Okay. So that's sort of like the picture that we're seeing. And so what we're seeing here is that this is Q enclosed, and this is definitely going to be smaller, which is Q total. So we see that we enclosed partial charge. So we know that the enclosed charge must be smaller. Okay, so now let's look at the Gaussian. The Gaussian is again a cylinder. This immediately tells me that I know the flux of a cylinder, right? There's the end pieces plus the curved walls. We saw from the previous discussion that this guy is automatically zero because E and DA are perpendicular to each other. So when I look at this flux here, it's only due to the curved walls. Now, I don't really want to draw the E field, but I'm going to draw them here, just a few of them. This is the direction of the E field coming out of the Gaussian surface here, right? It's poking out of that Gaussian surface. I don't want to sort of like put too much there. So then when I look at this guy, this immediately tells me that, again, I get a positive charge. Why? Because DA and E are parallel. So then I have the E field of little r, and then I have the area of the curved walls. So immediately I know what the flux is, right? Immediately we know the flux. So now our job here is to get the enclosed charge. The enclosed charge is the charge within the cylindrical, Gaussian. And we can clearly see from the picture here that Q enclosed has to be smaller than Q. Right? So it is smaller, right? It is smaller than the total charge. So here we go. So the charge density equation reads like this. It says that rho is a constant. And if it's a constant, it has to be the total charge over the total volume. And this doesn't matter how we cut it up. Since it's a uniform charge distribution, it always has to look like this here. So now what we're going to do here is that we're going to solve for Q enclosed. So if I do that, I then see that Q enclosed is then going to be the ratio of what? The enclosed volume over the total volume of the cylinder times the total charge. Now, what's the volume of a cylinder? So we just looked at the area up here, and it is the circumference times the length. Now, to get the volume of a cylinder, we now know here. So the volume of a cylinder, by the way, you might say like, well, of course we know the volume of a cylinder. I'll tell you this, that's one of the most common mistakes on the quizzes and exam. People have no idea what the volume of a cylinder versus a sphere, and they mix them up. So if you feel like I'm insulting, my apologies. I just know experience of, 33 years in academia. So here I go. So if I take the cylinder now, it has to be what? This is the area of this guy, which has to be pi r squared. And then I got to multiply this by the length. So the volume of a cylinder is then pi r squared times L. So here I go. So then Q enclosed tells me what? It's going to be my enclosed volume. Well, that has to be pi r squared times L. And then look at my Gaussian, right? The Gaussian has little r. Look at the total cylinder has a radius of big R. So then this has to be pi r big R squared times L times the total charge. And you can clearly see that this guy, the lengths cancel out. And you also see that the pi's cancel out. So then I have a ratio of r squared, big R squared times Q, and this is Q enclosed. So now I have Q enclosed. So I have the flux, I have the charge density, and it looks like this. So if I now put this together, Gauss's law tells us what? It says that the flux of the cylinder must be Q enclosed times epsilon naught. So therefore, I know that this is going to be plus E of little r less than big R times the area of the Gaussian surface. And then Q enclosed then is going to be little r, big R squared Q times 1 over epsilon naught. So when the dust settles here, we could then solve for the electric field here, and I'm going to get 2 pi epsilon naught. I'm going to get r squared, and then I'm going to get Q divided by L times little r, which is also 2 pi epsilon r squared lambda times r. So this is my Gaussian, my E field produced on that Gaussian surface right there. So what I want to do now is that I want to summarize this and plot it. So what I'm saying here is that in summary, we have the following thing. If we are inside the cylinder, it looks like this. So it's 2 pi epsilon r squared times lambda times little r. And if you're outside, it's lambda over 2 pi epsilon r. And this is for little r less than big R and little r greater than big R. And then this is the field of a charged cylinder. So when I look at this thing, this is what it looks like. So now what I want to do here is I want to plot this. Okay, let's plot the field. So what I have here is I have an insulating charged cylinder. So when I draw this, it looks like this. So I'm going to draw just a quarter of it. Okay, so here's my cylinder here. And so when I look at my charge, it looks like this. So now my E field looks something like this. So I look at my E field, and I'm going to be plotting this guy, where this distance is my distance big R. And here's my field. Now, if I look at this thing, look at what happens. Inside the cylinder, it goes linear. Note that this is very similar to what happened with an insulating spherical sphere. And so what you're seeing here is that as the Gaussian surface gets smaller and smaller, it encloses less and less charge. And therefore, I have zero enclosed charge at the center, and the field should be zero. Exactly what we would expect. And then it falls off. It has a stronger field than a shell, excuse me, a sphere, because you could see that outside it falls off as what? It falls off as E proportional to 1 over R. And then here, the field is proportional to R. So when you're looking at the outside of the field, you're seeing that the field is stronger for a cylinder than it is for a sphere. So there's a couple of things here. So immediately what you're seeing here is that you're seeing that it's discontinuous at the surface. No surprise. So that means that the E field, the perpendicular component on the inside, is not the same as the field as the outside. Okay. And another thing here is that note that you have maximum strength at the surface. And another thing that we should say here is that it's a good thing that E inside is proportional to R. And what that says here is that as R gets smaller, the Gaussian encloses less and less charge. At the center, Q enclosed is equal to 0, and so E field at the center is equal to 0, too. Now, why am I making a point about this? If the E field inside was equal to the E field of outside, which would have been lambda 2 pi epsilon R, then the limit as R goes to 0 of the field inside would then be the limit as R goes to 0 of 2 pi lambda R divided into lambda. And you could see here is that this goes to infinite. So we are saved that the field does not behave the same as the outside, because otherwise, again, this means we have a problem. We have a problem if the field was the same as the outside, but it's not.